yesterday. All right. So section 4.1 is on maximum and minimum values of a function. And yesterday we talked about the difference between an absolute maximum, absolute minimum, local maximum, local minimum. Okay. So, I mean, I'm just going to make this up off the top of my head so we can just review. But here's the graph of a function f of x over some closed interval, in this case a to b. And the absolute maximum of this function, right, is the largest y coordinate, right, the largest function value. And so in this case, the absolute maximum is f of b. The absolute minimum occurs at the minimum y coordinate, which is down here, right, the lowest point on the graph. And so if this occurs at x equals c, okay, then the absolute minimum, right, is the value of the function f of c. Okay. The local maximums occur at the tops of hills, tops of mountains, right? You can have a peak. Okay. And so here's the top of the hill. So let's say that top of the hill occurs at x equals d. Okay. So for this problem that I just made up off the top of my head, there's only one local maximum, and that value is f of d. Okay. There are two local minimums in this problem. So let's call this, say, here's the local, right? The local minimums are at the bottom of the hills. So we have a local minimum here at x equals c, and one at x equals. So we have a local minimum value of f of c and f of b. Okay. So you notice that at x equals c, we have both a absolute minimum and a local minimum. Okay. You can have both, but you can only have one value for the absolute minimum. Okay. And only one value for the absolute maximum. Although the absolute minimum may occur for more than one value of x, and the absolute maximum may occur for more than one value of x. But you can only have one value for the absolute minimum, and only one value for the absolute maximum. Okay.
So f of a wouldn't be a local maximum?
No. And the reason for that, okay, from our definition, definition 4.1.2, okay, is that, and the textbooks used to word it this way, but it's for it to be a local maximum, right? The value of the function has to be greater than all the values of the function for x near there, but it has to be to the left and to the right, and there's nothing to the left. Okay, so endpoints don't count for local minimums and local maximums.
But they do count for absolutes.
Yeah, this guy's an endpoint, right? X equals b is an endpoint of the interval, and this is where the absolute maximum is. Okay. it can't be a local maximum because it has to be for an interval where B is in an open interval, right? Where B is in the open interval. Okay. Your textbook just says for values of X near B. Older textbooks talked about an open interval that contains B. Okay. So it has to have our local maximum, right? This is a local maximum. That's for values of X greater than D, and for values of X less than D, this function value is greater than the neighboring function values. Okay. All right. It's a good question. Any other questions? So this is sort of a quick review of what we did yesterday. Okay. So let's move on. And now we're going to talk about the extreme value theorem. So if our function f is continuous on a closed interval from A to B, okay? So you know closed intervals include the endpoints, right? Open intervals don't include the endpoints, okay? So if f is continuous on a closed interval from A to B, then f attains an absolute maximum value f of c and an absolute minimum value f of d at some numbers c and d in the closed interval. So I'll draw a picture, and this is like intuitively makes a lot of sense. Okay. If f is continuous on a closed interval from A to B, then f attains an absolute maximum value, f of c, and an absolute minimum value, f of d, at some numbers c and d in the closed interval. Okay. So let me draw a graph that meets these conditions. So most of my graphing, you know, I tend to do just in the first quadrant. Okay. So it's a closed interval from A to B, right? The closed interval applies to the variable x, right? It says x is greater than or equal to A and less than or equal to B. Okay. And our function f of x is continuous from x equals A to x equals B. So here's an example function, okay, that is continuous from x equals a to x equals b, right? Remember, from your high school algebra, right, if it's continuous, you can trace out the graph of the function without lifting your pencil off the paper, right? And you can see that this is the case here, right? We can trace out the graph of f of x from x equals a to x equals b without lifting our pencil off the paper, okay? And so if that condition is true, okay, then somewhere between x equals a to x equals b, the function has to attain an absolute maximum, and somewhere it has to attain an absolute minimum, just by virtue of it being continuous from x equals a to x equals b. Okay. And so you can see in this arbitrary graph that I've drawn here, the highest point on the graph, right, we'll label it occurring at x equals c. And this point on the graph, right, has an x coordinate of c and a y coordinate of f of c. So the absolute maximum value of the function in this example is f of c. Okay. And the lowest point on the graph, right, occurs here. We'll say that occurs at x equals d. And the point on the graph, the lowest point on the graph there, right, has coordinates d and f of d. Okay. So f of c is the absolute maximum value of the function, and f of d is the absolute minimum value of the function. Right? For this example, so by virtue of it being the function being continuous from x equals a to x equals b, there has to be an absolute maximum value, and there has to be an absolute minimum value. Yes, sir.
Would it be a straight line function with a slope of 0? Is that continuous or a straight line? It
Yeah.
wouldn't have an absolute.
Well, I guess it would be both, right?
If you consider, if it's considered.
Here's A, here's B. Right? And this is right, f of A, f of B, and right, everything has the same function value, right? And the definition for an absolute maximum, right, the first one we put up was that, so this is pick a point called C, f of C has to be greater than or equal to f of x for greater than or equal to f of x for all values of x near C, right? And then for the absolute minimum, f of C has to be less than or equal to f of x, right? It's not strictly less than, it's not strictly greater than. Yeah. Okay.
It doesn't need to. It doesn't have to be unique. If you extended a sine wave forever, it would just be. You'd have multiple peaks that are all the same. They're all hitting the absolute maximum value.
Yeah. Absolute maximum can occur at more than one value of x.
Yeah.
Okay, remember that absolute max and absolute min, local max, local min are function values. They're y coordinates, not x coordinates, right? And that's probably the most hardest thing to remember, right? Is these absolute max and min, local max and min are function values, right? Not x coordinates. Okay. any other questions on that? All right, let's move on to the next theorem. And this is called, I don't know how to pronounce this name. I think it's French, I can't remember. Fermat's, something like that. Fermat's theorem. If f has a local maximum or minimum at x equals c, okay? And this is an important condition. And if the derivative of f of x at x equals c, so f prime of c exists, I'll double underline that, right? Because I can't do bold on the board. Okay. The derivative has a, you know that some derivatives, right? The derivative for some functions doesn't exist at some values of x. Okay. And if f prime of c exists, then the value of the derivative at x equals c must be 0. So I'm going to steal my graph over here, but take away the labeling on the x-axis. Okay. And I am going to keep the labeling here, right? This is C, this is D. Okay. And the graph doesn't have to end there. It could continue on, right, both directions. What's interesting, what I'm pointing out, what's important here is this has a local maximum and a local minimum. Okay. So if f has a local maximum or minimum at x equals c, so in this case at x equals c, it's a local maximum. And if the first derivative exists, and you can see it does because it's a smooth curve, right? It's not pointed, not a mountaintop. Okay. Then this derivative, the derivative at x equals c has to be 0. Okay. That's what Fermat's theorem is saying. Okay. So you can see at this local maximum, the tangent line is horizontal. Okay. And the slope of the tangent line is equal to the derivative of the function. Well, the slope of the tangent line is 0, and it's equal to the derivative of the function at x equals c. So we have to have f prime of c is equal to 0. And similarly, at this local minimum, the slope of the tangent line is 0. Right, smooth curve, right, so the derivative exists. The slope of the tangent line is 0. The slope of the tangent line is equal to the derivative of the function at x equals d. So we have to have f prime of d is equal to 0. That's what Fermat's theorem is saying. Okay? If you have a local max or min at c and the derivative exists, then the value of the derivative has to be 0. Okay? It can't equal any other number. Okay? All right. So just to remind you, f prime of c and f prime of d give the slope of the tangent line. And the tangent line, right, when the derivative exists, is the slope of the tangent line is 0. Okay. All right. I need to give you a caution concerning this because you can misinterpret this theorem. If the derivative of f of x at x equals c is equal to 0, that does not mean there's a local maximum or local minimum. That does not guarantee there's a local maximum or local minimum at that point. This says if there's a local maximum or minimum at x equals c and the derivative exists, then the derivative at x equals c has to be 0. You can't do the reverse. You can't conclude if the derivative equals 0, then there's a local maximum or minimum at c. Okay. We'll demonstrate that with an example. F of x is equal to x to the 5th plus 7. Okay. F prime of x in this case, we know is equal to 5x to the 4th, right? Derivative of x to the 5th with respect to x is 5x to the 5th, or 5x to the 4th, and derivative plus 7 is 0. And when I put 0 in for x, I have f prime of 0 is equal to 5 times 0 to the 4th, which is equal to 0. So at x equals 0, the derivative is equal to 0. Okay. But the function f of x has no local maximum or minimum at x equals 0 because the graph of this function, x to the 5th plus 7, crosses the y-axis at x equals 7, and it's similar to the cubing function. Right, it snakes across the y-axis at x at y equals 7. Right, you can see the y-intercept. You put in 0 for x, you get 0 to the 5th plus 7, which is 7. So at y equals 7, it crosses the y-axis. And at that point, at y equals 7, the horizontal, right, the tangent line has a slope of 0. F prime of 0 is equal to 0. Okay? The slope of the tangent line is 0, but that's not a local maximum or minimum. Okay? So you can have points on the graph of a smooth function, okay, where the slope is 0, but it's not a local maximum or local minimum. Okay? So you can't conclude that because the derivative at a value of x equals 0 that we're going to have a local maximum or local minimum. Okay? F has no local maximum or minimum. Okay? Doesn't even have an absolute maximum or minimum in this case. Okay? Any questions on the caution? Okay. All right. So next, let's talk about critical numbers. So this is definition 4.1.6. Critical numbers, right, is important. So a critical number from calculus of a function f is a number c in the domain of f such that either of the following two conditions is true. Okay. Either f prime of c is equal to 0, right? The value of the derivative at x equals c is 0, or the value of the derivative at x equals c does not exist. So I'll double underline that. Okay. Critical number, right? So critical numbers are values of x. Okay. Critical numbers are values of x, right? The input variable x. Okay. And there are those values of x in the domain of the function f, where the first derivative is equal to 0, or the first derivative does not exist. So we'll demonstrate this concept with a couple examples. So in the first example, we have f of x is equal to x cubed minus 3x squared minus 24x plus 92. So you might recognize this as a third-degree polynomial. All polynomials, right, are continuous. They're nice, smooth curves. They're differentiable. Okay. So to find the critical numbers of f of x, first we got to differentiate it. Get its first derivative, f prime of x. Well, derivative of x cubed is 3x squared. Derivative of minus 3x squared is minus 6x. Derivative of minus 24x is minus 24. And then derivative plus 92 is 0. Okay. So critical number of a function f is a number c in the domain of f such that either the first derivative at x equals c is 0, or the first derivative at x equals c does not exist. So to find the critical numbers, we set f prime of x equal to 0 and solve for x. Okay. So we have 3x squared minus 6x minus 24 is equal to 0. Now you'll notice, right, this is a quadratic on the left-hand side, and the coefficients 3 minus 6, and minus 24 are all divisible by 3. So I'm going to divide both sides in 0 divided by 3 is 0. So I'm going to divide both sides by 3 to reduce those coefficients. I have x squared minus 2x minus 8 is equal to 0. Okay. So when I divide each term by 3, right? You follow what I just did? Okay. And now it makes it easier for me to factor. Okay. And so the left-hand side factors into x plus 2 times x minus 4. And then by the zero product property, okay, a product of two factors is equal to 0. So either the first factor, x plus 2 is equal to 0, or the second factor, x minus 4 is equal to 0. And now when I solve for x, I get x is equal to minus 2, and x is equal to 4. So these two values of x are the critical numbers of f of x. Okay? Those are the two values of x that make the first derivative equal to 0. Okay? So these are the critical numbers of our function f. Okay? Any questions on that? All right, now, does this mean there's a local maximum or local minimum at x equals minus 2 or x equals 4? So that was the caveat, the caution from the previous theorem, right? So there might be a local max or min at x equals minus 2, and there might be one at x equals 4. Okay? Or you might have a situation where we had with x to the 5th, right? Where the slope is 0, okay? It's for some value of x, but it's not a local max or a local min. Okay? So you can't tell at this stage. You just know they're critical numbers. Okay? They make the first derivative equal to 0. All right, in the next example, we have g of x is equal to the cube root of x. And you know, cube root of x can be written as x to the 1/3 power. And now to find the critical numbers, right, we differentiate. We have g prime of x is equal to 1/3 times x to the minus 2/3 power. Right, just using the power rule. Well, x to the minus 2/3 is equal to 1 over x to the plus 2/3, right? Well, g prime of 0, right, the value of the first derivative, x equals 0, is equal to 1 over 3 times 0 to the 2/3 power. Well, 0 to the 2/3 power is 0. 0 times 3 is 0. So this is equal to 1 over 0, which is undefined. So g prime of x, the first derivative, is undefined at x equals 0. So that, right, so the first derivative, x equals 0, does not exist So that makes x equals 0 a critical number. It's the only critical number, g of x. There's no number you can put in for x that'll make this equal to 0. All right. So finding critical numbers, you gotta find the values of x that make the first derivative equal to 0, and or make the first derivative undefined. Okay. Any questions on that, ladies and gentlemen? Yes, Sahar.
So how come for the first example you set f of x equal to 0, whereas for this one you just set x equal to 0? Why'd you do that instead of setting?
Well, I can tell right off the bat that if I set that equals 0, there's no number I can put in for x that makes that equal to 0. The only way, right, the only way the derivative can equal 0 is if you got x in the numerator, and there's no x in the numerator. And I did it by inspection, that if I put 0 in for x, the denominator would be 0. Okay. Any other questions?
So in layman's term, critical number, what we're looking for is we're looking for when the function changes direction, if we're to graph it. I mean, that's what these places did.
I don't know if the function, because right, the example I did where it crossed at y equals 7, right?
Yeah.
It came up, flattened out, kept on going up.
Yeah.
So it's not necessarily changing direction.
So then why do we care about it?
Huh?
Why are we interested in it?
Well,
We'll find out.
you'll find out.
Next episode.
Okay. I mean, there's a lot of use for critical numbers. Okay.
I would hope so.
So, I mean, one of the things we're going to use them for is to find the local maximums and the local minimums. Okay. And where the graph of a function, we're also, the derivative is going to help us find where the graph is going up, where it's going down, things of that nature. Okay. But at the end of the day, right, one thing that we're interested in, where are the local maximums, where are the local minimums, and the derivative is 0 at those points.
Yeah, I guess the set of all the critical numbers will have all of the maximums in them. You know, it's not one to one. They're going to be in there.
Mm-hmm. That's right. Where either it's undefined or where it's equal to 0. Right? Critical numbers, basically, let me rephrase that. Critical numbers occur when the derivative is equal to 0 or undefined. Right? Does not exist. So the local maximums will occur in there. Yep. All right. But for some of those critical numbers, there may not be a local max or a min. Okay. Any other questions? Okay. All right, next definition. If f has a local maximum, or minimum at x equals c, okay, then c is a critical number of f. Okay. Does just sort of reversing the logic, right? If f has a local maximum or a local minimum, then in this case, the derivative in both those places would be 0, and that would make those two values critical numbers. Okay. So let me give you a graphical demonstration. So here's my function f of x. And this is, I drew this one yesterday. Okay. So in this case, it's going up to the left on the right. Right? It's going up to the left. It's going up on the left and going down on the right. Okay. And so at this point right here, right, it's differentiable. This is a smooth curve. And the slope of the tangent line is 0. Okay. And so I labeled this point at x equals c. And so we have f prime of c is equal to 0, right, at that point. Now, at the mountaintop, this is like a mountaintop, right, a peak point. So say that occurs at x equals d. You know the function's not differentiable at x equals d, right, because it's pointing. And so f prime of d does not exist. This is the local minimum because it's the bottom of a hill, and this is the local maximum because it's the top of a mountain peak. Okay. So local minimum, local maximum, derivative is equal to 0 here, derivative does not exist there. So C and D are both critical numbers. So C and D are critical numbers. C makes the first derivative equal to 0, and D at x equals D, the derivative does not exist. Okay. All right. Any questions on that? All right. Final topic from this section. Okay. Given a function on a closed interval, how do you find the absolute maximum and absolute minimum? Okay. I just started erasing that. I hope that was okay. Can I erase the graph? Back in the olden days, when I was your age taking Calc 1, the professor was so fast writing on the board. He'd be writing on that end of the board, and I'd still be copying up here on the far left. Yeah, it was like that. All right. So now we're going to talk how to find the absolute maximum, absolute minimum of a function on a closed interval. This is called the closed interval method. Okay. It's not a very catchy title. Okay. Alright, so to find the absolute maximum and minimum values of a continuous function A to B. Remember, on closed intervals, we include the endpoints, right? We include A, we include B. Okay. So I'll just write that out. The input variable X includes A and B, right? X is greater than or equal to A and less than or equal to B. Okay. 3 steps. Step number 1. Find the values of F at the critical numbers of F in the open interval from A to B. Okay. So open interval does not include the endpoints. Okay. So this is for X greater than A and less, and strictly less than B. Step number 2. Find the values of F at the endpoints of the interval. So there we're finding F of A and F of B. Okay? A and B are the endpoints of the interval. The largest of the values from step 1 and step 2 is the absolute maximum value. So we calculate the value of the function at each of the critical numbers, and the value of the function at the left endpoint and the right endpoint, and then we take the largest of those values to get the absolute maximum value. Okay. The smallest then of these values is the absolute minimum value. Okay. So we calculate the value of the function at each of the critical numbers, the value of the function at the left endpoint and the right endpoint. The largest value from that set of numbers is the absolute maximum value, and the smallest from that set of numbers is the absolute minimum value. So any questions on this 3-step process for finding the absolute max, absolute min over an interval? So let's do an example. Actually, so Harvey, did you get your picture?
I did, yeah.
Can I erase this?
Oh, yeah.
Is everybody still copying? For once, going twice. So the first example, f of x is equal to the polynomial 4x cubed plus 9x squared minus 12x plus 1. In the interval, the closed interval goes from -1 to 2. And for emphasis, we're talking about the values of x in the function go from -1 to 2. So from x equals -1 to x equals 2, where's the absolute maximum? What's the absolute maximum? What's the absolute minimum value? Okay. So step number 1, find the critical numbers. So f prime of x, in this case, derivative 4x cubed is 12x squared. Derivative 9x squared is 18x. Derivative of minus 12x is minus 12. Derivative constant is 0. Okay. Now we set the first derivative equal to 0 and solve for x, right? To get the critical numbers. So we have 12x squared plus 18x minus 12 is equal to 0. 12 and 18 are both divisible by 6. So I'm going to divide the left-hand side, right, all three of those terms by 6 to simplify the problem. And I have 2x squared plus 3x minus 2 is equal to 0. Now it's quadratic. Factor the left-hand side. Get the values of x that make the left-hand side equal to 0. And the left-hand side factors into 2x minus 1 times x plus 2. So by the zero product property, either 2x minus 1 is equal to 0, or x plus 2 is equal to 0. And solving for x, we get x is equal to 1/2. X is equal to minus 2. There's one small issue with our answer here for x. What is it? Does anybody notice? Pardon?
It's not within a closed interval.
Yeah, minus 2 is not between minus 1 and 2, right? So minus x and minus 2 is not a critical number of this function over this in this interval. Okay. For x equals minus 1 to plus 2. So there's only one critical number. X equals 1/2. So next step, evaluate the function at the critical number 1/2 and at the endpoints, minus 1 and 2. Okay. Now this is just a Robert Bell thing. You don't have to do it this way. But I always list out the endpoints and the critical numbers in sequential order. I mean, it's just a Robert Bell thing. So I have f of minus 1, I have f of 1/2, and I have f of 2. You don't have to write them out in this order. Okay? You write them out in any order you want. Okay? But we got to evaluate the function at the left endpoint minus 1, the right endpoint x equals 2, and the one critical number in that interval x equals 1/2. Okay? So we have 4. So f of minus 1. 4 times minus 1 cubed plus 9 times minus 1 squared minus 12 times minus 1 plus 1 And when I did all that arithmetic, right, now you gotta do PEMDAS. When I did all that arithmetic, I got 18. So the value of the function f at x equals minus 1 is 18. F of 1/2, right? Now you gotta deal with fractions. 4 times 1/2 cubed plus 9 times 1/2 squared minus 12 times 1/2 plus 1. And when I perform PEMDAS, right, common denominator, right, and all that stuff, I got minus 19/4 for the value of the function at x equals 1/2. F of 2, put 2 in for x. You have 4 times 2 cubed plus 9 times 2 squared minus 12 times 2 plus 1. And again, right, following order of operations, I got 45 for the value of the function at x equals 2. So what's the absolute maximum value of this function on that interval? 45, right? This is the absolute maximum value. What's the absolute minimum value? It would be this guy, right? It's negative. That's positive. So this is the absolute minimum value. And we're done. Any questions on that? Yes, ma'am.
Does the 18 correspond to anything, or is that just so that we can find?
It's not the, I mean, we had to evaluate the function at the left endpoint,
Oh, okay.
right? So you evaluate the function at the left endpoint, the right endpoint, and then the critical numbers. In the next example, we have f of x is equal to 1/4 x plus x to the minus 1 power. And this is over the interval from 1 to 3, right? The closed interval from 1 to 3. Right, so that means it's for x greater than or equal to 1 and less than or equal to 3. Same process as in the previous example. But you're going to do it yourself. We'll compare answers in class tomorrow. First thing. Okay. All right, so let me get attendance.